Hello and welcome to lecture on T1, T2, and T2star for UCSF Biomedical Imaging 201 Principles of MRI. And this is Chapter 4 in MRI, the basics. Starting off with today, arguably very creepy MRI picture of the day of a sedated cat in a MRI system here, looking pretty anesthetized. We can see here the different inputs to the RF coil numbered here: 1, 2, 3, 4, 5, 6, 7, 8. So presumably an 8-channel RF coil that they're using for this study. Okay, the goals listed here for today. Really, the title captures it all. We're looking at T1, T2, T2star, equilibrium, and dephasing are two concepts that I'll introduce here, but you also want to make sure to understand. So, relaxation is the term that we use in MRI for T1, T2, and T2star. So, what does relaxation mean? Does it mean relaxation? Breathe in, breathe out. Well, maybe for the spins. Or my personal favorite here, this looks like relaxation to me. I could probably lie down like this right now. So at these, get to the point of what is relaxation? Relaxation is returning to the lowest energy state or the equilibrium state of the system. So arguably that cat, I would say, was at the lowest energy state. It was at some sort of equilibrium. So in MRI, relaxation is the process by which the net magnetization, which recall is the source of all of our signal in MRI, it's the process by which it returns to equilibrium. And if you recall from the earlier lectures, what is equilibrium? Equilibrium is the net magnetization oriented in alignment with B0, our main magnetic field, which by convention is our z-axis, and with an amplitude of m0. This is defined to be the equilibrium magnetization. And the process of relaxation by which the net magnetization returns to equilibrium is actually a very important source of contrast in MRI. That's why this is introduced very early in this textbook. And so this is an animation illustrating the process of relaxation. So we can see there was, in the very beginning of this animation, there was an RF pulse that perturbed the net magnetization from equilibrium, which is the state that you saw at the beginning, pointed along the z-axis, the white vector here being the net magnetization. And this sort of shrinking and growing process that you're seeing, is happening due to T1 and T2 relaxation in this simulation. So another way of looking at the process of the relaxation is drawn here. So in this picture, the black arrow is our net magnetization, and it's been deflected by an RF pulse away from orientation with B0, the main field, and so it's going to return to equilibrium in alignment with B0 over time. It's going to return to having an amplitude of m0, and we break this up into two relaxation times or two relaxation processes. First of those listed at the bottom here is T1, which has a couple different names. I usually refer to this as the longitudinal relaxation time. So longitudinal also referring to our MZ, our Z magnetization. The second of these processes is T2, the transverse relaxation time is the term that I like to use, or it's referring to the transverse component. And this is another reason why we're going to divide up our net magnetization into the Z longitudinal and the transverse MXY components here. And then at the end here, after we've undergone enough time, we'll be back in our happy state here of the lowest energy equilibrium. So this process of relaxation is an incredible source of contrast in MRI. So these would be typical images you'd get from a brain study. The proton density, this is basically the M0 weighted imaging. And we discussed this briefly in the initial lecture, and this is simply related to the number of protons, the number of spins that we've got contributing to our net magnetization, which then contributes to our image. But we can also create images that are weighted by, for example, T1 or T2. You can see very clearly by these top row of images here that you're getting quite different contrast. You're going to pick up very different types of pathologies or tissue properties by doing proton density versus T1 versus T2 weighted imaging here. So they're really, all three are, particularly T1 and T2, are very important for clinical imaging. And the example at the bottom is showing a case of contrast agent, which these gadolinium chelates that are the most common MRI contrast agent. And these actually act to change this T1 relaxation time. So this is another example where relaxation is what is important for creating MRI contrast. So to assess how relaxation works, we can come back to our first principles equation of MRI, the Bloch equation. And when we were talking about RF pulses, we were just looking at the first term here, this vector cross product between the net magnetization vector and the magnetic field vector. Now, for the purposes of looking at relaxation, we're going to neglect or take out this term, and this is a valid assumption to make, both when there's no RF pulse being applied, as well as if we assume that we are in the rotating frame of observation, which for the majority of the following lectures, I will assume that we're in the rotating frame for sort of ease of generating intuition. So then we're left with just the other side of this differential equation, this term that includes these minus 1 over T2, minus 1 over T1, and also M0 over T1. So it includes our relaxation times T1 and T2, and also our equilibrium magnetization M0. And in fact, this is a much simpler differential equation here, where on the left side, our change in the magnetic field over time is proportional to the the change in net magnetization over time is proportional to the net magnetization multiplied by these relaxation terms, as well as the term that's going to account for the return of the equilibrium. So it's actually quite straightforward to solve this type of differential equation. So I'm presenting you here with the solutions that now we will use in solving problems in MRI. And what you see here, the first is the solution for the transverse or MXY component of the net magnetization, where the transverse magnetization over time will depend on what the initial transverse magnetization was, MXY 0, and then with this exponential decay term, e to the minus t over t2. And note that this definition repeated here again, that the transverse magnetization, MXY, is defined as the x component of the net magnetization vector plus I times the y component of the magnetization vector, which is a very convenient notation. And relaxation, in fact, is one of the reasons why we separate it, take our net magnetization vector, which has x, y, and z, and kind of do this grouping of x, y versus z. Okay, and then at the bottom here, the solution for the longitudinal or z component of the net magnetization. Over time, it's going to depend on the initial value of the longitudinal magnetization multiplied by this e to the minus t over t1 term. And then the next term here is sort of a recovery term. It's the equilibrium magnetization M0 multiplied by 1 minus e to the minus t over T1. Okay, and we'll draw some pictures of what these equations look like. We have exponential rates of change here according to the T2 and T1 times. So let's start off with T1 relaxation. The term I prefer is the longitudinal relaxation time, though a lot of coming from NMR in particular. This is often sometimes called the thermal relaxation time or the spin lattice relaxation time. And this is governing the longitudinal component, governing the return to equilibrium or lowest energy state. Where the spin lattice term comes from is that this is the time that it takes for the spins. If you think about it in a quantum mechanical sense, looking at individual spins, that they give their energy that they got from the RF pulse, they're going to give this energy back to the surrounding lattice. And that's as deep as I will go into that explanation when we're looking at this classically, as we do with the net magnetization vector. We won't address the sort of lattice. Now I want to make a quick comment here in the two lectures forward from this, so chapter 6, we'll discuss some of the mechanisms that govern both T1 and T2, so what tissues have different T1 and T2 values. But here we're going to focus on just the their behavior on the net magnetization. So this is what the illustration of the T1 relaxation, here with our drawing on the left showing the orientation of B0, the main magnetic field. And if we start off with the Z magnetization that is smaller than M0, then we will, over time, it will return to this amplitude of M0. So this would be M0 up here. And in this case, an example at the right is a plot of this exponential T1 recovery. So we see that in the asymptote here, it is going to reach the M0 value. And this is the solution for a particular case where our MZ at time 0 is equal to 0. And, later on, I'll show some examples of, well, if this is not true. In general, you can see from this equation that these e to the minus t over t1 terms, they become 0 as t grows and grows. And so you're always just left with m0 times 1, or just m0 over time. And here we are back at m0, relaxed. This is showing the process of T1 relaxation, this 3D animation here, the net magnetization. And so what we can see when I get this going here, and as here, we're just looking at the longitudinal component. We'll bring in the transverse component after we talk about T2. And so this is just a vector illustration of what's happening. And again, in this case, where we're starting with 0 Z magnetization. Just let that go one more time. Okay, now let's move on to T2 relaxation. The name that I prefer for this is the transverse relaxation time. This is because T2 is acting on the XY, or the transverse component of the net magnetization. But this is also commonly referred to as the spin-spin relaxation time, and I'll briefly discuss why that term is used. And that's because of these mechanisms listed there, that the spins basically experience slightly different magnetic fields, and in fact, due to the magnetic fields that they create, right? Each spin is a little magnet. It's going to create its own little magnetic field, and these magnetic fields between the spins are going to interact with each other and lead to this T2 relaxation effect, which we can describe by the incoherent phase that exists between spins. And I'll unpack that statement in the coming slides here. So looking at know what the effect here is on the net magnetization vector. Now suppose in this other example we start with the net magnetization here pointed in the perpendicular plane to B naught. So we have some transverse magnetization, or MXY, and over time this MXY becomes 0. So no matter what value it starts off at, it becomes 0 in the end. And this is because our relaxation state here, you can see the XY term in the net magnetization vector at sleeping kitty state here is 0 and 0. So we have to relax back to 0 and X and Y. And you can see that in this exponential decay curve. This is plotted for, in fact, some arbitrary MXY0. So this is simply whatever value we are at the start here. And illustrated through this 3D animation of a net magnetization vector. And so here we're just looking at the transverse component. You can look at these two, the longitudinal and transverse components separately. In fact, that's what these two solutions to the Bloch equation tell us we can do. And then we'll put them back together in just a moment here. We can just take a second to enjoy that we basically have this transverse component going away, and this is what the exponential decay rate looks like when visualized as the net magnetization vector. Okay, as promised, we're going to combine T1 and T2 relaxation here. Okay, and so now what happens is we see I put a little RF pulse in there to tip. It's so fast that you can hardly see it, but it's tipping the net magnetization away from the z-axis. And we're at equilibrium along the z-axis. And so the net magnetization goes through this relaxation process. Now both T1 and T2 simply and clearly described by the relaxation equations listed at the bottom. And you can see at the end, we're always going towards this orientation along the z-axis, returning to M naught, or the equilibrium magnetization value. A couple of notes to make about T1 and T2. First of all, for physical reasons, T2 is always less than or equal to T1. And the other thing you can note from this that is the amplitude of the net magnetization is actually changing during relaxation here. So this is a common misconception or a common error that can happen in understanding the magnetization vector. You can see my pen here. It's not like illustration where the net magnetization is always the same length and it's sort of moving around or relaxing back like in some manner like this. It's actually the amplitude is going to be changing size, just as you see in this animation here. So I'm going to spend a couple of slides going into the mechanism as to what causes T2. And this, I'm going to introduce this concept of dephasing. And this concept of dephasing is going to come up in several different ways throughout the understanding of the principles of MRI. And here's the first way that it comes up. So I want to introduce what I mean by dephasing. Okay, so suppose we have a set of spins here. These are, remember, hydrogen atoms, likely in water. They're close to each other, maybe even on the same water molecule or just sitting nearby. And because each of these spins creates its own little magnetic field, there's actually a slightly different magnetic field for each of these spins. Okay, and that's what's noted here by this delta BZ1, 2, and 3. This is there to say that each one of these spins has a slightly different magnetic field it's experiencing. So recalling from the fundamental principles of resonance is that remember when our spins are in a magnetic field, they're going to precess or rotate at a rate that's proportional to the magnetic field. And initially we said, well, the magnetic field is just B0 everywhere. Now we're really looking at a very microscopic sort of atomic level here, or molecular level, and saying, well, there's actually subtle variations in the magnetic field between spins. And so these different spins then are going to actually rotate at these slightly different frequencies. Here I'm taking the rotating frame perspective. So this means they're normally, if there's this, they're all at the same magnetic field, they're not going to change, but they're at slightly different magnetic fields. So now we have a condition where these spins have a slightly different resonant frequency due to these local molecular level changes in the magnetic field. And when we look at then the net magnetization, that's the sum of all these individual spins here. And the fact that they're spreading out and being oriented at different angles, in fact, impacts the net magnetization. So that I aim to show in the next slide here. So this slide is showing that, remember that our net magnetization is the sum over all of our spins in some small volume. And normally, if all of our spins are aligned in the same direction, and or have a slight preference to be aligned in the same direction, they're going to add up coherently. But now, if these spins are precessing at slightly different rates, that's going to create this incoherence or this dephasing phenomenon. And this is what the illustration now on the bottom right is trying to show us, the dephasing. So meaning when they have different angles or different phases between these spins, then they're going to add together incoherently. And this is the concept I mean by dephasing. And so this is basically what's happening in T2. Now we can also use this concept, and even more so, and to understand T2star relaxation. So what is T2star relaxation? T2star relaxation is a combination of T2, which is our spin-spin dephasing. These are molecular level inhomogeneities that lead to these spins becoming out of alignment. T2star is happening on a larger scale, what I call a macroscopic scale, on the order of our imaging voxel size. So on the micron or millimeter scale. And we're going to write this, the equation for this to be that our T2star relaxation time, or if we take the inverse, then it becomes a rate. It's going to be equal to relaxation due to T2 plus some additional relaxation that is often notated as T2 prime. And this is the intra-voxel or the within voxel dephasing that's going to happen and actually cause our signal to decay at an even faster rate. And so what this equation is going to tell us is one principle, that T2 star is always less than or equal to T2. So what causes T2 star? Again, it's these T2 decay plus this macroscopic dephasing. So I've taken the same illustration, and we can use this to understand T2 star as well. But now I specifically drawn this not as the individual spins, which is the level at which T2 happens, but as net magnetizations. And it's a larger scale. So we've already sort of had to sum over our individual spins to create net magnetizations. Now we're going to have to look at the level of the net magnetization to look at this effect. And then I've got this voxel drawing over here because this is really an effect that we consider on the order of our imaging voxels or our voxel elements. So, for example, if I'm looking at across the voxel, I might have some net magnetization at one position, at another position in the voxel, which can have a slightly different magnetic field. We want to look at the net magnetization there, and so forth, right? And so this simple illustration, we'll just consider an example of 3 positions within this voxel. And just like the T2 dephasing example, we're going to consider that each of these net magnetizations within our voxel are experiencing a slightly different magnetic field. And they are experiencing a different magnetic field not because of just the neighboring spins, the molecules nearby, but they're seeing a different magnetic field for other reasons. So these are different magnetic fields due to differences in, say, magnetic susceptibility. So the presence of iron, calcium, gadolinium, even air nearby will change the magnetic field. And also, we assume that our B0 field is homogeneous. We'd like it to be perfect across our entire subject, but in reality, it's not quite perfect, and so there are some imperfections. We can wrap those into T2star here. And so now, because of these changes in the magnetic field, since the resonance frequency is proportional to the magnetic field, we're going to get slightly different rates of rotation or frequencies due to the different magnetic field experienced by each of these net magnetizations. And then when we measure the signal across this entire voxel, which is the smallest element that we can decompose our signal into, we're going to get the T2 decay. So you see I've drawn these arrows such that they're actually shrinking. That's the T2 decay, and then the rotation here, the extra rotation due to the different frequencies, the sometimes called off resonance frequencies, is going to lead to additional signal loss or this additional dephasing. So again, we can look at this dephasing from the perspective of the fact that, again, our smallest unit of measurement that we get in an image is over an imaging voxel. Then that's the definition of the voxel. It's the smallest thing we measure. Okay, so we're going to get a measurement that's always the sum or the average across this. So that's why I have this notation MXY voxel here. It's representing the sum of the transverse magnetization across the voxel, and that's the smallest thing we can see. And again, we're thinking of, okay, we're observing one location here and another location down here with a slightly different, that experiences a slightly different magnetic field. And this example, a third location experiences yet a slightly different magnetic field due to these effects, likely due to magnetic susceptibility properties. And because they have different frequencies and they're rotating at different rates, they're going to add to each other incoherently and lead to this overall decay of the signal. And so that is illustrated here by the fact that their sum of the MXY voxel has gotten smaller over time due to the fact that they're rotating at different rates, so they have different phases, or that's where the term dephasing comes into play. And there's also T2, and if we were to have no intravoxel dephasing, if we have a perfectly homogeneous magnetic field within our imaging voxel, we would get a case like I'm going to show on the next slide, which is like this. So here we do have all the net magnetizations shrinking due to T2 decay, but no additional rotations due to local changes in the magnetic field. So if you look back at the previous slide, you'll see that the MXY voxel, which is going to be the signal we're going to get in our image in this voxel, is going to be larger in this case when we don't have this dephasing, we don't have any variations in the magnetic field across the voxel. Compared to when we do have these variations, we do have these changes in magnetic field across the voxel, we're going to get some shrinking of the MXY across the voxel, or some loss in signal, in fact. And another way to illustrate that is to look at the signal over time in a voxel in a couple different ways. So we can say we're just looking at, or the transverse magnetization, say we're just looking at the transverse magnetization here from a single location. That transverse magnetization is going to decay with time constant T2. But now, if we're looking at the signal across our entire voxel, then we're going to get some accelerated decay due to this dephasing. And I'm going to draw it specifically here in this pattern here to have a little bit of oscillation. And that's because when we have the phenomenon, the changes across the voxel that lead to T2star accelerated decay, we don't necessarily get an exponential pattern. It really depends on what's the variation in the magnetic field across this voxel, and we approximate it as an exponential decay. So we're going to say this is approximately some exponential decay with the time constant T2 star, but it's not exactly. So, a pure exponential decay would look something like that. We're going to approximate it to be exponential for simplicity. So T2 and T2 star, actually we can access both of these types of relaxation to create image contrast. So in the way so far that we've covered to generate MRI signal, that we require an RF pulse and acquire signal. This is often referred to as a gradient echo or gradient recalled echo sequence that we'll cover in more detail later on. This type of sequence gets a T2 star weighted image contrast. But we can, in fact, access T2. We can get rid of these effects this T2 prime, these effects that cause additional dephasing in T2 star. And we do that through the use of spin echo pulse sequences, which will be covered in chapter 8. And there's some fundamental differences between T2 and T2 star related to the fact that T2 is happening at this intramolecular level, that we cannot undo the changes that are happening at this level between our spins, but we can undo the changes that are happening between our net magnetizations at the voxel level. Okay, so that's it for this chapter on T1, T2, and T2 star. And these are relaxation phenomena. We also covered equilibrium and this concept of dephasing that's going to come up again in our understanding of MRI. So thank you for watching.